may have noticed I took the liberty of including IMPA in my affiliation there. It's a lifelong dream of mine to be associated at least for a longer period of time with IMPA, so I just did that. So what I want to talk about today is some aspects of this theory that I've been working on for a little over 10 years now. It started out as a rather simple-minded set of questions. Okay, malfunction already. What do I do? Oh, okay. Upside down, okay. And the pretentious way of stating it is like that. So the program is to understand all the analytic, geometric, dynamical, and topological mechanisms that ensure the global invertibility of local diffeomorphisms between non-compact manifolds. As I said, when I started out working on this problem, I just had a few remarks that I had made, and I couldn't dream that, upon further examination, I would be looking into all these aspects. But it was a pleasant surprise that indeed the subject or the program connects with many different areas of mathematics. And so, for instance, our inquiries are guided by all these problems, which work more as signposts than anything else. The famous Jacobian conjecture in algebraic geometry, which asserts that if you have a polynomial local biholomorphism from Cn into itself, it's automatically bijective. What used to be the Marcos-Yamabe conjecture in dynamical systems, solved by Fessler, Glatziuk, and the late Gutierrez. The study of the group of automorphisms of Cn for n bigger than 1 is a wide open area. There's a problem coming from mathematical economics that seems to be attracting a lot of attention too. And another topic which is very interesting would be to try to classify the conformal harmonic embeddings of R2 into R3. These would be, the images which are simply connected. The images would be simply connected embedded parabolic minimal surfaces. And here, of course, what comes to mind immediately is the great work of Harold and Bill Meeks, characterizing the properly embedded, complete simply connected minimal surfaces as being the helicoids in the plane. Here, I would drop the properness or completeness assumption and deal just with the conformal structure. Notice that this is not really a problem of the type that I stated there because the dimensions are different, but nevertheless, there is sort of a general set of ideas or mindset even that applies to many of these problems. So in the long-term goal would be actually to do something in infinite dimensions to try to understand these mechanisms better in infinite dimensions with a view towards applying these results to nonlinear analysis problems in PDEs. So if time allows, I'll even give an example of this type at the end of the talk. So since I'm in the business also of advertising this theory, let me list some of these the results that we obtained along the years, and I'll give you a very, very brief description. I'll be talking about generalizations of the first one there. Okay, so I'll leave that aside for a while. The second one has to do with the interaction of this problem about understanding injective holomorphic mappings and some topology. I may even sketch the simple argument in a moment, the one that originated the entire paper. In the third reference, we're interested in extending to general conformal immersions the basic Bieber-Bach estimates from the theory of univalent functions of one complex variables. Again, with a view towards perhaps understanding this embeddedness question for conformal maps. In part 4, we look at what happens with the singular set of a possible counterexample of the Jacobian conjecture. So the techniques there involve topology and algebraic geometry. By the way, because of my nomadic interest or nature, mathematical nature, I was forced, so to speak, to work with people from other than differential geometers. Some of them are algebraic geometers, others are topologists. Reference 5 there it's a study of the rigidity of the identity map in Cn among all injective holomorphic mappings. So using some classical ideas of Kronwall and Bieberbach. And the last part is really geometry. So what we do there is we use some geometric inequalities to extend the usual intersection properties of affine hyperplanes to the nonlinear setting. So in a way, it's like creating a nonlinear version of linear algebra. Okay, but today's work is really about the first one there, global inversion via the Palais-Mail condition. And what we're going to do is to cast this theorem, this result, which is written there, I'll say a few words about it in a second, in a differential geometric framework. The result was for Rn only. And along the way, we'll improve the regularity of the result. So what the theorem says is that if you have a map, it's perhaps even better to look at the statement as in the bottom there. So a local diffeomorphism C21 is bijective if for all non-zero v's that function satisfies the Palais-Mail condition. Okay, so for instance, I'll be saying a little bit about the Palais-Mail condition in a second. Okay. Or if you prefer, just look at the statement as is. So star there, of course, stands for the transpose. So if for each fixed v, the infimum of the action of the transposes of the differential on v is positive, v being non-zero, of course, then the map is automatically bijective. Okay. So now I'm sort of trying to move horizontally and vertically there. So after we suitably reinterpret the basic techniques that went into that paper, we can move horizontally and try to extend the result to the case when the target is a Cartan-Hadamard manifold. That's the work with Lee. Gang Lee, by the way, my co-author there, he's a graduate student at Notre Dame. He's not a student of mine. He's a student of a friend of mine. That's not a practice that I would recommend for everybody to raid on, on your friends, graduate students, but only if you're in good terms with the advisor. Okay, and the second part is to extend the result to infinite dimensions. So some of the techniques, as you see, the basic ideas will work to prove invertibility results for nonlinear Fredholm operators on banach spaces. And that's work that I'm writing up as we speak. So a very brief review. Cartan-Hadamard manifold is a simply connected Riemannian manifold with sectional curvature being non-positive everywhere. And an important part of the study of these things is the compactification at infinity obtained by considering equivalence classes of geodesic rays that remain at a bounded distance of each other. So that gives for you this ideal boundary, and it comes with a natural topology. And for each point on the manifold, there is a canonical identification between the unit tangent sphere at that point and the sphere at infinity. So these are all An important notion is the idea of a Boltzmann function. So I'm sure you've all seen how that's defined. So Boltzmann functions, they are replacements or they generalize the idea of linear functionals in Euclidean space. So they are convex functions, they have gradient 1, and they are C2. Okay? So some Horo-entities. So level sets are, for a fixed point at infinity, are V Horo spheres. Set of that nature, sublevel set, is a V Horo ball. And if you take the union, the region between two Horo balls, you get what naturally should be called a V Horo annulus. So here, here's the main theorem, okay? So which generalizes the result that I mentioned of Notre and myself. So what it says is that you have a map. So here you have your manifold N. You look at the point at infinity. Look at some V Horo annulus here. So M is over here. So you take a point f of x in there. Okay. Here you have the tangent vector corresponding to V. I'll just denote it by V itself. Okay. Now you take the transpose of this vector, so that's back into the tangent space of X. Okay. Take the norm there, and now take the infimum over all points in the preimage of this horosphere. Okay. So if it turns out that for every choice of point at infinity V and every horoannulus AV, if that's positive, then that's enough to guarantee that the map is a diffeomorphism. I'll try to unwind this a little bit better as we go along. Okay. So for instance, if both manifolds are the same Cartan-Hadamard manifold, and if you take an isometry, then the condition is clearly satisfied. You always get one. Okay? And isometries, of course, are bijective. So in a way, the main point of the theorem is exactly the fact that to get invertibility, you don't need a positive lower bound over all product space there. So it's just necessary that you get one positive lower bound for each V and each horoannulus there. Okay, and it's easy to illustrate this already in Rn. I'll give you examples later. Now, weaker but aesthetically pleasing. Now, the action of the transpose at this vector that corresponds to V there is nothing but the gradient or the negative of the gradient of the composition of the Boltzmann function with the map. So now we get to a much more manageable and easier to remember statement, which again, logically speaking, is weaker than the previous one, but it's much more pleasing. So the test is this. If you have a map from M into a Hadamard manifold, if you know that every time you compose with a Boltzmann function, the infimum of the differential is positive, then F is a C1 diffeomorphism. Okay, so it's a simple test. So if you apply this in the case of Rn, what you have is, so in Rn, a V horoannulus is simply the region between two hyperplanes perpendicular to V. So this improves the original result. Okay? So the original result, I mean the one of Notre and myself in Rn, so TM1 actually should be thought of as being some kind of generalized Palais-Mail condition for these functionals there. The composition of the Boltzmann functions with the map. So again, once again, the idea is that when you go to the nonlinear world of a Hadamard manifold, the place of the linear functionals is taken now by Boltzmann functions. Okay, so let me give you some applications in flat spaces. This is somewhat surprising. So there are applications that are new even for flat space. Okay, and the issue of global invertibility of maps has an impact actually on the question of existence and uniqueness of critical points of functions in Rn. Okay, so just to give you some idea, let's begin with this innocuous statement here. So suppose that you have a C2 function, and it's such that the Hessian never vanishes on a non-zero vector. That is to say, the Hessian is everywhere a non-singular operator, right? So certainly, by the Morse lemma, if you have a critical point, the critical point will be non-degenerate and therefore isolated. So what you can say right away is that if you have this simple-minded condition there, then this set of critical points is at most countable. And the point of this particular consequence of our theorem is that if you strengthen this suitably, you can drastically reduce the size of the critical set. So here's the theorem, sort of striking. So if for each V, if you take the infimum of the Hessian of F over all X in Rn, apply that V, if that's positive, then there is precisely one critical point. Okay? Now, the numbers themselves, I mean, they may very well vary with V. If you were to take the infimum, a double infimum now over V having norm 1, this double infimum could be 0. Okay? And we also get a complementary result of the following type. Suppose you have a C2 function, which again enjoys this property that the Hessian is nowhere degenerate. And if this function happens to be the C1 local uniform limit of functions satisfying the hypothesis of the previous theorem, then G has at most one critical point. And it turns out that this class contains all C2 strictly convex functions. Okay? So in other words, we all know that if you have a C2 strictly convex function, it can have at most 2 points. At most one critical point. It could have none and could have one. And this, so somehow these ideas create for you, out of the blue, a class that's richer than the class of convex functions. Okay? Now the proof of the theorem is rather easy. What you want to do is you want to, of this last theorem that is, what you want to do is you want to create, you want to look at the gradient map and apply the theorem, right? So the gradient map ends up being bijective, and in particular 0 is covered exactly once. And so that means that there's just one critical point. And for the corollary, you do some appropriate approximation argument. It would be very interesting actually to extend this result to general Hadamard manifolds, but I thought about it a little bit, but there doesn't seem to be a reasonable notion of a gradient map for a Hadamard manifold. I mean, if you're given a function, how do you create a gradient map? Well, you can do parallel translation back and forth, and you can do certain things that formally, when you specialize to the case of Rn, will give you back the original, the standard gradient map. But it's hard to compute with those things, and in particular, it's not at all clear what happens when you take the Hessian of the original function, how that relates to the differential of this map. So that's sort of an interesting question. Now, if a corollary of all this would be the following: take a C2 function on Rn and look at the set of all eigenvalues formed by of the Hessian. Okay, so collect them all. So it could be even a disconnected set. So suppose that you have gaps, right? So you have a gap. So either there is no negative part, within a gap, or there's no positive part So you can isolate the set by some interval minus delta 0 or 0 delta. If you have these two things, then F has precisely one critical point. Now, if you instead of and you say or, then it has at most one critical point. Okay, and and the consequence of this is that you can characterize Euclidean flat space among other complete flat manifolds by the property that it carries a C2 function for which the absolute value of the eigenvalues of the Hessian are uniformly bounded away from 0. Okay. So in here I'm just writing down for you the aspect that the general theorem takes if you look at the Poincare plane, Poincare disk. Okay, it looks imposing, of course, but there's no way around. I mean, you're taking pre-images of Horo-annulus and all that, but just keep in mind that isometries satisfy that, isometries of the Poincare metric. Okay. So, in a way, the theorem is really interesting when you take n equals 2 because you have a much finer characterization of Möbius maps. Okay, but that would take us more in the direction of complex analysis, and I don't want to do that. So, excuse me. So the point of this theorem is that it represents quite a considerable improvement, at least in finite dimensions, of the classical Hadamard global inverse function theorem. So let me just restate that for you here. So if you take a banach space and you take a map, which is a local diffeomorphism there, C1 local diffeomorphism, and if the inverse of the differential is uniformly bounded above or equivalent, if this is bounded from below, then the map is actually a diffeomorphism. Okay. Nowadays, the ideas that go into this thing are the same ideas that go into proving that the exponential map of a Hadamard manifold is a diffeomorphism. I don't know historically how these things happen. Perhaps I should, have looked at Hadamard's collected works before giving the talk. But so, how does the Hadamard condition look like on Hadamard manifolds? So the the natural version. So let's rewrite this. So you can make a simple moves here, and the Hadamard condition becomes a double infimum. See? And which at least formally is much more restricted than the single infimum, right, condition, which is the hypothesis of the theorem 2, which itself was a special case of our main theorem. But let's just hold on to this more palatable version, okay? Namely, every time you compose the map with a Boltzmann function, the differential is uniformly bounded from below, okay? So you have one bullet and two bullets. So let's compare the two bullets. So the proof of the Hadamard condition involves very simple-minded path-lifting arguments. It's really, nowadays it's quite trivial, at least morally, because what you want is you want to be able to lift any path. So let's say you're given beta t, and you want to find the lift of that. So just differentiate. So it turns out that what you want is just be able to solve this equation for all times, right? You want to lift the entire path. So one way to do this is simply to bound this. So that's all there is to it. Back in the days of Hadamard, perhaps, they hadn't reached this degree of clarity yet. But anyway, so the proof of two bullets, which is theorem 2, right, This is rather more complicated. So it involves ideas that come from dynamical systems and topological methods from nonlinear analysis, pseudo-gradients, degree theory, things like that. And the proof is conceptually similar to what's called the shooting method in two-point boundary value problems for second-order ODEs. So I hope to say a few words about that. But then, still with this theme, one bullet or two bullets. See, one might be tempted to argue with the compactness of the sphere at infinity, that if the single infimum condition holds, then so does the double infimum condition. Let me go back here again. So see, you have the single infimum condition here, over here, for each zeta in the sphere at infinity. But this guy is compact, so, naive idea would be just to say, well, if you take another infimum here, since this is compact, everything would be fine, and maybe 2 would be just as good as 1. But then, of course, the flaw is that the single infimum, as viewed as a function of zeta, may not vary continuously. Okay? So here's an example. So 2 is actually better than 1. So, so just take this very simple map here where f of x, so there's a comma there, f of x is any smooth function whose derivative is surjective. So in particular, this map f can have arbitrarily large growth. Okay? So you can actually see by hand that this map is invertible, that is the inverse here, and you can actually compute these things, and that's what you get. You get 1 for the infimum if you are at one of these 2 points here, and V2 if V2 is non-zero. And the function is, the double infimum is clearly 0 because of this, and it's discontinuous. Okay? So our theorem is truly a much better result than what you'd be getting from this classical Hadamard theorem, which is used in analysis, actually. Now, the version of the argument of Hadamard that we're most used to is, of course, the one from differential geometry. And so even the classical theorem in differential geometry that the exponential map is a diffeomorphism for a Cauchy-Hadamard manifold, that's also embedded, so to speak, in this framework here. It's actually a consequence of this bigger theorem. You can do a little fiddling around here and get to the condition. In this case, of course, regardless of the sphere at the point at infinity, you get a uniform lower bound for the composition of the Boltzmann function in the exponential map. Okay, and remember that the whole thing is the flexibility that you get from that theorem there, right? That number, all you require is that it be positive, but it may vary a lot. Even for the same fixed point at infinity v, it could vary considerably if you just change the Horo-entities and, let alone varying the point v itself along the sphere at infinity. Okay, now, turns out that the story behind these analytic theorems is actually quite remarkable. They are both our theorem, and I'm talking now about the first theorem with Notre, not this extension to Hadamard manifolds. So that theorem, which in itself already extends Hadamard's theorem in finite dimensions, they turned out to be just analytic manifestations of a certain topological phenomena. So Balheira was a graduate student of mine. This one was truly a student of mine. So it turns out that the ultimate test, so to speak, for whether or not the local diffeomorphism for Rn into itself is bijective is what happens to the preimage of hyperplanes. If every time you pull back a hyperplane, you get a set which is non-empty and acyclic, So it has the homology of a point. Let's say diffeomorphic to Rn minus 1. Then the map is injective, is bijective actually. So it's this test, and just look at all these pullbacks and check the topology, and then somehow the map is reassembled nicely into a bijection. Okay. Now the analog of his theorem in our context would be, one could ask, well, maybe what's going on is, if you replace the domain Rn there by a complete Riemannian manifold and the target Rn by an arbitrary Cartan-Hadamard manifold, maybe the test is that the preimage of every Horo cycle, okay, should be acyclic. But if that's the case, then this of course would subsume the theorem that I stated here, my theorem with gang Lie. The difficulty with trying to do this, and there are many difficulties. First of all, the construction that Cabral Barreira uses is quite sophisticated, very geometric, and it depends on taking the pullbacks of whole families of foliations by hyperplanes, and the fact that they somehow these families vary smoothly. Now, in the context of Hadamard manifolds, that would be general ones. That would be very hard, if not impossible, to do, for the fact that the sphere at infinity does not have a smooth structure. So you don't know how to vary in a smooth way these Horo cycles.
Thank you.
Yep.
Where are the hyperplanes enter in that statement? I mean, you have a foliation, a smooth foliation, but you also have a foliation by spheres, for example.
Mm-hmm.
So why hyperplanes?
In his theorem?
Yeah.
Well, I guess I would have to give you the construction. If you give me 2 minutes, I will sketch the construction. Okay. So it's a very ingenious geometric construction. So very roughly, suppose you have 2 points that are mapped into this point here. So you want to reach a contradiction. So take a small neighborhood here, and so since the map is a local diffeomorphism, you have corresponding neighborhoods here and here. Okay. Now take a line. Let me do it for R3. Okay. Take a line here and look at the cylinder. Which has, which is tangent to this little ball there. So the idea is, you now take hyperplanes that are tangent to the equator here. So what happens there? Well, the point of tangency is going to have 2 corresponding points over here and over here, right? And so the preimage is connected for one. So you have some kind of surface like that. So go ahead and join these 2 points. Okay. Now by a it's not hard to imagine that if you just so the idea now is to rotate these planes around. Okay. So if you rotate just a little bit, it's not hard to imagine that you can generate some kind of a little bend like this, just by making a small perturbation. Okay, so you do this in the neighborhood of every point in the parameter space. The parameter space being the circle there. Okay, and by compactness you get finitely many intervals where you cover. Now at these points where the intervals meet, okay, you have like your choice of curve will be double valued, right? Because you know, when you go from one to the other, you don't know really how you chose that. So what you get at this stage is you get this gap here, okay? Now, since you're assuming that the preimage is simply connected, in this case, you can fill it inside the preimage of the appropriate hyperplane with a disk, okay? So now you do this all around. So at the end of the day, what you get is something that looks like this, okay? And actually, you do these things with the ultimate argument involves intersection numbers of cycles. So the object doesn't need to be a manifold as such, but roughly speaking, you get this. So now you put a little cap in here, another cap in there, and starts lifting the axis. So what happens when you try to lift the axis through here? Okay. So remember, there are 2 points in the preimage, right? These points go into this now. So let's say when you start lifting it up, that's the direction that you go inside this sausage-like figure. Okay. Now you had already exit, so to speak, or had come from the outside. So now you're lifting this, and so you may not be able to lift the entire axis, of course. But if that doesn't happen, that doesn't matter. What it means is that the lift has rushed off to infinity in finite time. So the point is that the lift, the maximal lift, will be some kind of so it will be a properly embedded curve, right? So the question now is, well, since this is an enclosed region, so to speak, this sausage, the lift must exit somewhere else. Where does it exit? It cannot exit on the outside, I claim, because the points here, they all came from these curves, and these curves, when you take their images, they actually lie in these tangent planes, which do not intersect the axis, right? So therefore, they don't exit there, so they must exit on the other cap. But what's happening then? So you start lifting this way, but when you get over here, this is back here. So you went up and then down. So that means that somewhere along this lift, the differential had become singular, contradicting the assumption that the map was everywhere a local diffeomorphism. In the higher dimensional case, it's much more complicated because you have to use simplicial decompositions, fill in with all kinds of lower dimensional objects, create these cycles, and so on and so forth. Okay. So now try to do this using general Hadamard manifolds. I guess we talked about that, didn't we? Okay. What's going on here? Oh, pointing up. Okay. Yes. So this is a general statement, which looks like a Palais-Mayo condition. The Palais-Mayo condition, remember, says, for instance, if you have a linear function on a banach space that let's say it's bounded from below, right? And if you have a sublevel set which contains a sequence of points where the differential of the functional is tending to 0, then such a sequence must have a convergent subsequence. So in particular, there is a critical point. Now in our context, our linear functions never have critical points because they are of the type df x star of something, of V, let's say, but the map is already a local diffeomorphism. So the condition that it's Palais-Mayo simply means that the infimum of the norm of the gradient is positive on every sublevel set. Okay, so now let me try to give you, I'm basically running out of time, so I'll just rush through some of the ideas here. So, a main difficulty is if you are working with C1 objects, is that the gradient is merely C0, so if you want to do some kind of flow argument, that's going to get into trouble because, you know, the flow is only continuous. You don't have uniqueness of solutions and so on. But there's a nice device which is the idea of pseudo-gradients, which gives you actually a smooth object, a smooth vector field, which retains the essential properties of the gradient. So it's you know, the norm is psi for pseudo. This is at most twice the norm of the gradient, and it kind of behaves like the gradient, right? If this was actually the gradient, this would be equal to without the 2 there. So that's enough to carry most of the constructions. And so the idea is you sit at a point, and then you take the flow, you fix a point at infinity, and you take the flow of that vector field there constructed from the pseudo-gradient. Notice that those kinds of guys are what you get from ordinary Morse theory, right? So that means that you're preserving the level somehow. Okay? And there's a great deal of estimates and homotopies that must be carefully chosen so that you can use the grid theory, you use the convexity of the Horo balls, etc., and you get surjectivity. The idea for injectivity is you know, try to select a Boltzmann function that separates the points. Again, it's this, you know, reminiscent of this idea from linear analysis, right? You know, if you want to separate points by a linear functional. So in this case, the role of linear functions is replaced by Boltzmann functions, and and then there's a mechanism which can be set up so as to reduce the injectivity issue to the surjectivity of a certain map. Surjectivity is easier than injectivity because you can use the grid theory to prove surjectivity. So you need to prove that for some point at infinity, some orbit, for some point at infinity, the orbit of the pseudo-gradient is going to pass through the 2 points, A and B, that you want to show that have distinct images. And, you know, once you have that's fine. Now, to actually achieving this is not so easy. There are certain things that must be looked into. There's a certain dynamical aspect of the whole thing, which is kind of reminiscent of appearance of rib foliations, rib components and foliations, things that go up and come back to the same place arbitrarily high. So you need to take care of those. And again, for that, you do more degree theory. You use the Leray product formula for degree, more convexity of Horo balls, more delicate estimates, more care with the homotopies not passing through the boundary, etc., and that's what you do. Now, so now in just 2 minutes, let me say what we can do in infinite dimensions. As I said, the original statement of myself and Notre extends greatly the finite dimensional version of the Hadamard theorem. Now, but even our theorem, which is this one here, see, in boldface, this fails miserably in infinite dimensions already for bounded linear maps, because if you have a bounded linear map on a banach space, I mean, the condition that this thing satisfies Palais-May for a bounded linear map, well, not Palais-May, that it be injective, would be simply that the adjoint is injective. But the adjoint of a linear map being injective only means that the range of the map itself is dense, you're very far from obtaining bijectivity. Okay, but it turns out that and this took me a long time to understand the process to go from finite to infinite dimensions, what was missing. So the challenges are sort of the usual ones: the lack of local compactness, possibility of defining topological degree for all continuous maps in infinite dimensions. But then there's a new dynamical phenomenon that appears in this lemma too, the one about being able to connect 2 points by some trajectory of some pseudo-gradient, which is kind of weird. But in any case, it is possible to state a theorem which is just like the finite dimensional versions of the Hadamard theorem, and it actually generalizes this known statement from Fredholm theory. If you have a linear compact perturbation of the identity, it's going to be invariable if the adjoint is injective. Well, the point is a compact perturbation of the identity is a Fredholm operator, so it has a closed range. If the adjoint is injective, then, as I pointed out, the range is dense, so since it was already closed, the map is now surjective, but then the index is 0. So being surjective means that it's injective. So that's what it is. So this is the statement. Let's just take 45 seconds to go through it. So in a banach space, C1 local diffeomorphism is bijective if K and the derivative map are completely continuous. So that means they apply bounded sets into pre-compact sets. For every sequence, you have this funny-looking condition here for every sequence. S star is the unit sphere. If you get a minimizing sequence like that, and this holds, then this has to converge. And the last one is the Palais-Mail condition. Okay. Now notice that in finite dimensions, all continuous maps are completely continuous. The second condition is certainly satisfied because, the unit sphere is compact there, so everything subconverges. So in finite dimensions, the only condition really that you have is the Palais-Mail condition, which is what I had advertised anyway. Okay, so that's what I was saying there. And let me draw attention to this.